Hello. In this video, I'm going to talk about tautologies and contradictions, the two main subjects of this section. If you haven't done so already, please read through the section and come back to this video when you're ready. Tautologies and contradictions, as you know now, tautology is a compound statement that's true for all possible values of its component statements. A contradiction is false for all possible values of its component statements. So two real easy examples of tautologies and contradictions are the following: P or not P, as well as P and not P. So P or not P, we don't necessarily have to use a truth table to figure out that this one is a tautology. So maybe P is the statement, it is raining, and then not P would be the statement, it is not raining. So P or not P would be the statement, it is raining or it is not raining, which of course, no matter if it's raining or not, one of the two has to be true. And so this is true no matter what truth value P is. So this is a tautology. Or we say it's tautological. It's a tautology. And similarly, it's raining and it's not raining. Well, that's doesn't make any sense, right? At any given place on Earth, at any given point in time, it's either raining or it's not raining, but not both at the same time, right? Again, a statement is a declarative sentence that's true or false, but not both. And here we have it's both true and false at the same time. So that doesn't make sense. This is a contradiction. There's no possible way to make this true. And we can look at a truth table for this. So let's do a truth table for P, both of these. We'd have P, we'd have not P, and then I'd want P or not P. As well, I would want P and not P. And let's just investigate these. So we have, two options for P. That's our only component statement here. Everything else is compound. So we have two options. It's either true or false. Not P would have the opposite truth value, and then we can compute P or not P. So right, P is either true or, and then not P would be false. So in this case, at least one of them is true. So that's true. Here again, at least one of them is true. And so P or not P is true. So it's true for every possible combination of the component statements. So this is what it looks like in a truth table to identify a tautology. You want every row to be true for that statement. Similarly, looking at P and not P, this should make sense why this is contradiction, because here it's true, false, false, true. So true, false, we take a conjunction of those. Well, they're not both true, so this is false, and same down there. They're not both true, so it's false. This is what we're looking for in a truth table to establish a contradiction, that you get false in every single row. So that's the idea of tautology contradiction. Let's take a look at a little bit more complex of an example, but not too complex. This is example 1.62 in our text. We have statements P and Q, and we can form the statement not Q or P implies Q. So this turns out to be a tautology, that this statement is always true no matter what P and Q are. We could show this with a truth table, and indeed, hopefully you're following along with the text. Hopefully you have your text right beside you. You can take a look at the truth table for that statement in this example and see that they're all true. But I want to offer another way to show that this is a tautology. So I want you to recall how we can rewrite implications. Recall that P implies Q is equivalent to not P or Q. Right? These are equivalent statements. And so that means I can rewrite this statement up here using this fact. So not Q or P implies Q is equivalent then to not Q or P implies Q, but here I'm going to write this like this, not P or Q. So now I have a disjunction of three statements, right? I can use associativity and commutativity to rewrite this to say Q or not Q. I'll group those together, or not P. And right here we have Q or not Q, and we just talked about the fact that this is tautological. This is a tautology. So this part of the disjunction is always true, and hence the disjunction, no matter what P is, the disjunction will always be true, because this term is always true. It's tautological. And so the original statement must also be a tautology. That's another way to see this one. Let's take a look at another one. This is example 1.63 from our text. P and Q implies not P. Again, you can look at the text, look at the truth table for this, and see that it's false for every combination of truth values of P and Q. Again, I want to offer a different take on this. How can you just look at this statement and figure out that, oh, this should be a contradiction without really having to look at a truth table? So you could do something like we did in the last example, rewrite this implication. You could do that, but I'm just going to think about this one. So P and Q implies not P. So I know, yeah, all three of those things. P, we have Q, and we have Q implies not P. So right, since we have Q, and we know that this implication is true, that Q implies not P, then we have that Q, we have Q, we know that Q implies not P, therefore we have not P, right? If Q is true, then not P must be true. Then we would have P and not P. So I could rewrite this to say P and not P, which we know is a contradiction. So that's one way to think about this, is that in order for this thing, I'll just leave it at that. Again, you can look at a truth table to see this. Maybe another way to think about this is with examples. Let's pick a P and a Q. Let's say P is the statement, it is raining. And Q is the statement, I go outside. So what this compound statement is saying is that it is raining, and I go outside, and what would Q implies not P be here? Q implies not P would be if I go outside, it's not raining. So again, okay, so it's raining, and I go outside, and if I go outside, then it's not raining. So, right, thinking about this again, well, if I go outside, it follows that it must not be raining. But I just said it was raining. And so it's raining and not raining at the same time. This doesn't make sense. There's no way for this to be true. This is false. And it doesn't matter what P and Q are. This is just always false. This is a contradiction. One way to think about it. And then jumping on to the next part of this are two commonly used tautologies. So one way to think about a tautology, it's like a theorem. It's like a law of logic that just works all the time. It's tautological. It's always true, and therefore we can always use it. So one example of that is Modus Ponens. So this one here is Modus Ponens. P and P implies Q. That whole thing implies Q. We actually used this law of logic, and you probably already used this law of logic. Maybe you haven't heard it called this, but you use this in your daily life all the time, right? If I know that something implies something else, and the condition, the hypothesis is satisfied, then I know the conclusion has to follow. That's all Modus Ponens is saying, right? I know that P implies Q, and I know that P is true. That is, the hypothesis is satisfied. Hence, the conclusion must follow. So all of this implies that the conclusion must follow. So again, P and P implies Q. That all implies Q. This is always true. So if we know implication is true and the hypothesis is satisfied, then the conclusion must follow. That's what Modus Ponens is saying. This is a tautology that always is true, no matter if P or Q is true or false, all possible combinations. We could also look at a truth table to verify that this is a tautology, but we don't really need to. Modus Ponens is sort of the reverse of this. This is another tautology. This is P implies Q and not Q all implies not P. So that is, if I know an implication's true and I know the conclusion is false, then it must be the case that the hypothesis was not satisfied, that the hypothesis is false. This is what Modus Ponens is saying. Again, we could look at a truth table for this if we wanted to verify this, but it should make sense why this is a tautology, why no matter what, this should be true, right? Implication's true, but I don't have the conclusion. Hence, I must not have triggered the cause, right? I must not have satisfied the hypothesis. So that's what's going on here. All right, that's about does it for section 1.5. I could kind of get all the material in one video here. Hopefully this helped you understand it a little bit better. See you in class.